Welcome back. In this segment, we're going to look at the atomic theory and how we've arrived at our understanding of the structure of matter at the level of atoms. Okay? So how did the atomic theory develop? It's actually a pretty long story, so I'll try to be brief here. It goes all the way back to the 4th century BC with a Greek philosopher known as Democritus. He's the first one that came up with this idea of an atom. In other words, that everything in the physical world is made up of these tiny, small objects that he referred to as atoms. In fact, that's where we get the name atom, coming over from the Greek. They can't be created, they can't be divided, they can't be destroyed, they're just there. And different types of matter are made up of different types of atoms. The properties of the materials that you see every day, well, that's because these particles give them their particular properties. And they're also constantly moving. There's also a problem with Democritus in that he had no real way of confirming the theory that he had. He believed that matter was eternal. That's all that they are. That's all existence is made up of these little particles. Okay? And so when you look at this little ball here in the middle of the screen, that's what Democritus said. At the end of the day, that's what everything is, are these tiny little balls that nobody can see. But we move on much further on in history to England. Again, in the 19th century, a man by the name of John Dalton, a chemist, very brilliant guy, was able to experimentally confirm a number of the ideas that Democritus proposed many centuries earlier. And it would include these. During chemical reactions, atoms of one element cannot be converted into another element. This idea that the alchemists had back in the Dark Ages, that you could turn lead somehow into gold. Well, no one ever did that. And the reason why is because it gets down to the structure of a lead atom and a gold atom. It's not possible to turn lead into gold or any other element for that matter. Atoms of the same element are identical, but they're different from other atoms. And they can combine in very specific ratios. For example, you know the chemical formula for water is H2O. You've probably known that for a long time. 2 parts of hydrogen atoms for every 1 part of the oxygen atoms. And we're able to experimentally confirm that for sure. All right, but then again, the structure of the atom for Dalton was basically the same as Democritus. You had these little balls. It was up until a couple decades later, J.J. Thompson, in the early 20th century, in his own experiments with a cathode ray tube, was able to come to a startling finding that had to do with these little structures. First off, what do we mean by a cathode ray tube? Well, you have a glass tube that has some phosphorus coated on one end. The air is sucked out, and if you run a very strong electric current through that, you can get this path of electric charge that lights up the screen at the end. Well, what Thompson did was he took a very strong electric field around that cathode ray tube that you see pictured here. He was actually able to deflect that path of light that shot up and lit up that part of the screen. And that led Thompson to infer that matter must have somehow a separation of charge, what we refer to now as positive and negative, these opposite charges that you see pictured here. And so when you begin to visualize what these little particles are, there's these negatively charged particles, and then we have, somehow they get balanced off in there. He referred to this as a plum pudding. Who eats plum pudding anyway? Well, how about thinking about a chocolate chip cookie? That works for you, doesn't it? So if these chocolate chips are actually representing, that looks good. These chocolate chips actually represent electrons that are surrounded by some positively charged material. That's kind of the idea that he had up until that. Now, it wasn't a whole lot longer in history that we go from Thomson's model of the atom to the one that you see pictured here, the planetary model. And that's due to one of Thompson's students, Ernest Rutherford, and his students as well. It led to the discovery of a much smaller center in atoms that's positively charged, that we now know as the nucleus. Well, how did that happen? Well, among the experiments that Ernest Rutherford did along with his students is that he took a very thin piece of gold foil. Think of the foil that's wrapped around your chewing gum, but much thinner. And it's made out of 24 karat gold. Very thin. What he did is he shot alpha particles through that gold foil, and the vast majority of those alpha particles just went straight through on this phosphorescent screen that you see going around the target. Most of those alpha particles just formed a bright spot on the opposite side. However, what surprised the researchers there is that there are some other bright spots, much smaller. These bright spots were coming off in all different directions. In fact, some of them were coming straight back at the source of the alpha particles. Well, how can that be? Rutherford and his students began to infer, therefore, that because alpha particles have a positive charge, there is a like charge, very, very small, but very strong, in the structure of the atoms. And so the atoms, therefore, must be mostly space because these alpha particles largely go through undeflected. But at the center of matter, these very incredibly small particles have to have a similar charge to the alpha particles, which was positive. He's inferring, therefore, what we now call to be the nucleus. So J.J. Thompson discovered the electrons, those negatively charged particles, and he's credited with naming those. Rutherford's work led to the discovery of protons and the discovery of the nucleus. So that's where we are here. Now, in terms of scale, I want you to imagine that if the whole atom is the size of this stadium, how large really is the nucleus inside that atom? Well, if we were to compare this, I want you to imagine, therefore, if you were to take a dime and place that dime on the 50-yard line of that football field, that's the nucleus. That's how small it is in comparison to the rest of the atom. So it's incredibly small. Okay? Now, we move on in our understanding, therefore, of the structure of the atom. We now have that idea of a planetary model. Now, of course, the nucleus is not drawn to scale here, but we have a strongly positively charged center around which these negatively charged electrons, which are almost massless, are going to revolve like the moon does around the Earth, like the Earth does around the sun. Hence the planetary model. Now, there's actually more to the modern theory of the structure of the atom, which I'll get into very briefly. There are actually many types of subatomic particles within atoms. But though in terms of usefulness in chemistry this year, we already really know what we need to know, and that's the protons, the neutrons, and the electrons. They're the ones that are really going to be most informative in terms of chemical processes this year. I have a chart that summarizes the essential information. What we've already mentioned, the protons and the neutrons make up the bulk of the mass of the atom. They're found inside the nucleus. The electrons are virtually massless in proportion, as you can see. We've adopted a new unit called the atomic mass unit, where the proton is essentially 1, and so are neutrons. When we look at the charges, the SI unit for charge is the coulomb, and you can see the proton and the electron, they have a similar but opposite charge. The neutrons have no charge, but they do account for a significant part of the mass of atoms. They're in the nucleus. So these are the essentials of what we're going to be looking at in terms of the structure of the atom. And then I want you to then begin to think about the structure of the atom, kind of like this picture here. The electrons are really kind of in a cloud that goes around this very dense positive center. And the reason why we describe it as a cloud is because we're really not exactly sure at any given instant in time where those electrons are. A fellow by the name of Heisenberg developed a principle that basically says that, well, we're never really going to be sure where these electrons are. We know they're there, but the only way that we can detect where they are is if we hit them with something. And once we hit them with something, they move. So they're not where we thought they were, only where they were, a millisecond ago. And so we now have, kind of a probability model of the electrons in this cloud that goes around the nucleus. We know where they are most of the time. They're close to the nucleus. And as you get further away, it's less likely that you're going to find them. And so we have an electron cloud model of the atom to think about. Now, that may be hard to grasp, and so I liken this model to getting a housefly and capturing it in a jar. Okay? So imagine that housefly there is an electron. Now, I'd like you to tell me, where's that fly going to be 3 seconds from now? Can you tell me that? Well, if this were a real fly, not just a photograph, you'd have a pretty difficult time because the motion of flies inside of jars, it's really quite unpredictable. That's kind of like what electrons are around the nucleus. We know the electrons are going to be around the nucleus, just like we know this fly is going to be in the jar. We just don't know exactly where. And so we've learned to deal with, this degree of uncertainty. Still, what we know about the structure of matter makes it extremely useful in predicting chemical reactions. And so we've come to, to be at peace with some degree of uncertainty in terms of the structure of matter. And what it comes down to really is this. We have these protons in the nucleus, and they're positively charged, and I liken them to the genes of the atom. The number of protons that you have in the nucleus is going to determine in large measure the number of electrons and the number of neutrons as well. They're going to follow pretty much line in line. There are atoms that can lose electrons temporarily. They can become electrically charged and become positive in their charge. Sometimes there are electrons that will take on extra electrons. For a period of time, they'll become negatively charged. We call each of those ions. And yet the structure here that you see pictured is really what we're going to be working with the remainder of the year. The electrons are going to revolve around a positively charged nucleus that you see pictured here. The atomic mass is basically the mass of the nucleus, which is the number of protons and neutrons. The electrons really not contributing that much to that. The reason why you see that it's a decimal here is largely due to the fact that not every carbon atom is going to have exactly the same number of neutrons. We refer to those as isotopes, which we'll get into later on. So this is really the useful information that you see pictured here regarding what we're going to use for chemistry throughout the remainder of the year. All right, now I want to leave you with one idea as we sum up the atomic theory. Have you ever seen an atom? Yeah, neither have I. We haven't seen these from Democritus up to the present time. No one's ever seen an atom, yet we have a large amount of evidence to show us what they are and how they're constructed, even though we've never seen them. And it's kind of like the existence of God. We reason on the existence of God in basically the same way. We look at the effect of what God has done in His creation, and we reason back to the efficient cause of all the effects that we see. Well, listen, it's been great looking at the atomic theory with you today. Thanks for watching. Bye-bye.